So we're talking again about the idea of a family of subsets being two colorable. So the definition of two colorable is it's a family of subsets of the numbers 1 up to n. All the subsets are the same size, such that in every subset I have at least one red and at least one blue. Okay, and this is for some coloring of the numbers 1 up to n. Okay, we saw before that if we take n to be 2d minus 1 and we take all the d element subsets, then f is not two colorable. Okay, that was by the pigeonhole principle. Now we're going to have a theorem that tells us when we can do it. So if f has not too many subsets, then it is two colorable. Notice that this remarkably doesn't depend on n. That's kind of amazing. Let's just do an example. Let's do an example to see. And let's do an example of d equal to 3. Okay, what is this statement saying in the case that d equals 3? We need to have f has less than 2 squared subsets. So it's going to have a, b, and c, all of size 3, okay? And we claim that it's two colorable, no matter what n is. But we can see that in this case, if we're going to have these 3 things, we're going to have n to be at least 4. So notice that n is at least 4. Otherwise, we can't take 3 different subsets. So why is this the case? So again, this says that there is some way to color the numbers 1, 2, 3, and 4. So we can again take our numbers 1, 2, 3, and 4. And we can think, okay, well, there are 2 different ways I could color them, right? And I can't see what my sets are, but there's got to be some way that I can color them so that A definitely ends up not all red and not all blue. B ends up not all red and not all blue, and C ends up not all red and not all blue. And again, I don't have visibility into what these sets are, so how can I prove such a thing? So we're going to do this as an example of a probabilistic proof, okay? So what I want to do is I want to think about what is the probability that, let's say, A is all red. This would be a bad thing to happen if the set A is all red. Well, A has 3 things inside of it, okay? And everything, if I think about it, I could think about randomly flipping a coin, and if it's heads, I pick the red, and if it's tails, I pick the blue. So the probability that the first number in A is red is going to be 1/2, because there's a 1/2 chance that it's red. And the second number, there's a 1/2 chance that it's red. And the third number, there's a 1/2 chance that it's red. So that gives me a total probability of 1 out of 8 that the set A is all red. Okay, so what is the probability that the set B, and again, I don't know which numbers are in here, but it doesn't matter, is all blue, or sorry, let's say A is all blue. Well, it's exactly the same argument, right? There's a 1/2 chance that the first letter of A, 1/2 for the second, 1/2 for the third. So it's 1/8. So let's bring this together. So what is the probability that A is monochromatic? So it's either all red or all blue. Well, this is 1/8 plus 1/8, which is 1/4. Okay, so there's a probability of 1/4. So for any random coloring of the numbers 1 to 4, or 1 up to n, it doesn't even matter how many numbers I have, there's a 1/4 probability that A is monochromatic. So the probability that A or B or C is monochromatic is equal to, well, it's at most, these aren't necessarily independent, but in the worst case they are, so it's at most 1/4 for A plus 1/4 for B plus 1/4 for C, which is equal to 3/4, which is strictly less than 1. So the probability that I have a monochromatic set is less than 1. That means it's possible that I don't. That means that there is a way to color F, right? A, B, C. There is a way to color these numbers so that none of these 3 is monochromatic. In fact, among all possible ways of coloring these numbers, I know that at least 1/4 of the ways of doing it is going to result in A, B, C, none of them being monochromatic. So this is an example of a probabilistic proof. I prove that something is not guaranteed, which means that the opposite of it is possible. And that proves it can happen, which proves that F is 2 colorable. Now, this has nothing to do with the number 3. So let me do this not in an example, but let's do it in more general terms. So here is a proof of this theorem. Again, ignoring this one example, how would we prove the theorem? Well, the probability that A, so some D set, is all red is equal to, there's a 1/2 chance that each letter in A is red, and there's a total of D letters in the set, because it's a D set. So that means that the probability that A is monochromatic, either red or blue, is going to be twice this. So it's 2 times 1/2 to the D, which is 1/2 to the D minus 1. Okay? Now, here's where I'm going to use the fact that I did not use too many sets. Okay? So the probability that one of less than 2D minus 1 sets in F is monochromatic is going to be less than or equal to the probability for each one, so it's going to be the sum over A is one of the sets in F, the probability that A is monochromatic. Okay? Now, what is that? Well, I've just figured out what this is. I know how many of these are. This doesn't depend on A, so this is going to be strictly less than the number of times that I have it, which is 2 to the D minus 1, times the probability for each one, which is 1/2 to the D minus 1, which is equal to 1. So because the probability is strictly less than 1, I know, oh, now it looks like less than or equal to. Because the probability is strictly less than 1, that means that there is some way to do it. So there is at least one way to two-color N for F. So there's at least one way to color the numbers 1 up to N with red and blue so that F has no monochromatic set. So we're going to use the same idea of a probabilistic argument to show that something is not guaranteed to happen in order to get a bound for Ramsey numbers. In this case, it'll be a lower bound.